Well, imagine trying to weigh a ghost. Or, I guess more accurately, imagine trying to measure the heat generated by a single microscopic whisper of quantum energy. That's essentially what we're looking at today. We are diving headfirst into a mind-bending breakthrough in quantum thermodynamics. It kind of feels like opening a cold case file where the clues are literally almost too small to exist in our physical reality.
So how exactly do you measure something that's practically not even there? To answer that, we're unpacking a brand new, frankly incredible research paper titled Zeptojoule calorimetry. It's led by Andres Martin Gunyaro alongside a team of researchers, and it was just published in the journal Nature Electronics. I want to treat this like the major news story it is because this study is basically breaking the news on how we might finally catch some of the most elusive energy signals in the entire universe.
But before we get into the how of it all, let's just try to wrap our heads around the what. 1 zeptojoule. That is 0 point followed by 20 zeros and then a 1 of a joule. To put that completely wild number into perspective, a single joule is roughly the amount of energy you'd use to lift a small apple about a meter off the ground. We are talking about a billionth of a trillionth of that apple lifting energy. It is just a spectacularly small amount of heat.
Now, the researchers over at Aalto University and VTT Technical Research Center in Finland, they didn't just sit around theorizing about this scale, they actually went ahead and built a device to measure it. And you might be wondering, why should we care about this right now? Well, it's absolutely crucial. Our ability to push quantum technology forward or even hunt for things like elusive dark matter is currently hitting a massive bottleneck simply because we can't detect these ultra-low energy microwave signals.
Right, so what is the actual problem that we're trying to solve here? Well, our current thermal detectors are amazing, don't get me wrong, but they completely hit a wall when it comes to catching very low-energy microwave photons. They just have this huge blind spot. Theoretically, the limits of our detection should really only be bounded by fundamental thermal fluctuations, but the reality in the microwave regime, which, by the way, is exactly where quantum computing operates, has just been this frustrating lack of sensitivity.
To get around this, the team realized they had to build a completely custom trap from scratch. What they designed is a highly specialized radiation sensor chip. You can sort of think of this entire setup as an incredibly delicate, microscopic net. It's explicitly engineered to catch those fleeting microwave pulses, convert them into a tiny bit of heat, and then measure them electrically.
If we zoom in on how this trap actually works, you'll find the real magic happening in a gold-palladium nanowire. And when I say nano, I mean it's barely 150 nanometers wide. When the microscopic energy of a microwave pulse hits this specific wire, it heats up. Just barely, but this tiny, tiny temperature spike changes the electrical properties of the entire circuit. Specifically, it shifts the resonance frequency of an oscillator attached to it. Basically, it acts as an unbelievably sensitive thermometer that registers the heat of just a few dozen photons.
But of course, there is a catch. The signal they get from that incredibly tiny heat spike is completely buried under a literal mountain of static. The raw data they collect is just a chaotic mess. So to find the actual signal, they use this really clever mathematical approach called matched filtering. It's kind of like knowing the exact shape of a fingerprint and then scanning a totally chaotic, messy room looking for just that one specific shape. By applying this filter, they were able to pull a clear, measurable signal right out of all that overwhelming noise.
Which brings us to the key result, and frankly, it is massive. They successfully measured 8.4 gigahertz microwave pulses with an energy resolution finer than 0.95 zeptojoules. And we can be really confident in this number because of their incredibly rigorous signal processing. In fact, their data suggests the resolution might even be finer than that. To put 0.95 zeptojoules into perspective again, that's equivalent to detecting a pulse made up of roughly 170 microscopic photons. They literally built a thermometer that measures the warmth of a handful of light particles. There's no way around it. That's just cool.
Now, to be fair, we do need to be honest about the limitations here. This isn't perfect yet. The device currently has a very narrow dynamic range, which basically means it maxes out after measuring just a few zeptojoules. It also relies heavily on all that complex digital filtering to even work, and right now its ultimate sensitivity is actually being limited by the noise coming from the external amplifiers they use rather than the sensor itself. So, it's a brilliant, groundbreaking step, but it is definitely an ongoing project.
So what does all of this actually mean for the future, in real, practical terms? Well, if we can scale this up and refine the tech, this tiny thermometer becomes a real game changer. It could allow us to read out the states of superconducting qubits with unprecedented accuracy. That alone could drive the next generation of quantum computers. But it could also give cosmologists a completely new, powerful way to hunt for axions, those theoretical particles that might just make up the dark matter in our universe. It's essentially unlocking a whole new level of perception for us.
And I think that leaves us with a really fascinating question to ponder as we wrap up this explainer. If we have now actually built the technology to truly feel the heat of a single quantum whisper, what other hidden secrets of the universe are we about to overhear next? Thanks so much for joining me today. Keep questioning the invisible, and I'll catch you next time.